2010 question 10A on antimatter. So in the first part of this question we're asked what is meant by pair production. So if we class that as part 1 in the question, this isn't the full question 10, this is only just focusing on the part on pair production. And the second part asks us to calculate the kinetic energy of one of the particles produced. So we're going to look at that in the second part. Okay, so for the first part, what is meant by pair production? Well, pair production is when a particle and an antiparticle, so we say pair production is when a particle and its antiparticle are produced from energy so in terms of if we were to draw that diagram, then what we would have here is a photon striking a nucleus, and then that energy that the photon has on striking the nucleus is converted into the two particles. So that energy is being converted into mass. But of course, charge has to be conserved and momentum is also conserved. So if we were to write an equation for this, then what we would say is that the energy of the photon is then given to the energy of the particles. So basically, we have conservation of energy here. So that energy that the photon has is going to be used then to make these particles. So the energy of a photon is given by HF, and then the energy gained to be converted into these positron and electron, or a particle and its antiparticle, would be RE equals mc squared. But because we have two particles, then each particle has its own energy. In other words, the energy is being converted into each mass. And then any excess energy, so if we just make the particles, but the particles don't move anywhere, then it would just be HF equals 2mc squared. But if there's any excess energy left over, then this is given by the kinetic energy of the two particles. So for part 2 of the question, because we're looking for the kinetic energy of one of the particles produced, then this energy here will be excess energy, will be gained by the two particles. In other words, the positron and the electron in the above diagram, or any particle and its antiparticle in any reaction where a particle and its antiparticle are produced in pair production. So here we're told that the frequency of the photon is 3.6 by 10 to the power 20 hertz, and that's what's causing the pair production. So if we look at the energy of the photon first, in other words, how much energy is there beforehand, then we'll have the energy of the photon is Planck's constant, which is h, so 6.6 by 10 to the power of minus 34 is given to us in the question, times f, the frequency, which is 3.6 by 10 to the power of 20, and that gives us an energy of, so 2.376 by 10 to the power of minus 13 joules. So this energy then is going to be converted into the mass to make the two particles, so the particle and the antiparticle. Now we're not told whether it's a positron and an electron in this case. Obviously in the diagram I've inserted here, it's an example of pair production. So what we are told is that each have a rest mass of 9.1 by 10 to the minus 31 kilograms. And obviously that is actually the rest mass of an electron. So if we look at the second part of the equation, in other words, the energy needed to make these particles, so E equals mc squared, but because the positron and the electron have the same mass, and if it was a particle and any antiparticle, it's either, or any particle and its antiparticle will always have the same mass anyway, so it's always going to be 2mc squared for this pair production. So what we have then is 2 times the mass, which is 9.1 by 10 to the power of minus 31, times the speed of light, which we were given to be 10 to the power of 3 by 10 to the power of 8. And we have to make sure that we square that. And then if we multiply that out, that gives us 1.638 by 10 to the power of minus 13 joules. So we can see clearly that there is a decrease in mass. So that means that there is more mass beforehand than there is afterwards. So therefore, because energy has to be conserved, the difference in the energy before and after will be the kinetic energy gained by the two particles. So the kinetic energy of the particles then will be the difference between 2.376 by 10 to the minus 13 minus 1.638 by 10 to the minus 13. And therefore, if I subtract those two values, I end up with 7.38 by 10 to the minus 14 joules. But because it's pair production and there are two particles, and if I go back up to the question here, it says what's the kinetic energy of one of the particles produced. So therefore this is for the two particles. So the particle and its antiparticle. So therefore we say the kinetic energy of one of the particles must be half of that value. So half of 7.38 by 10 to the power minus 14 is equal to 3.69 by 10 to the minus 14 joules. So there was 3 marks for working out the energy of the photon there, 3 marks for writing down R equals mc squared and making sure that we have that twice, 3 marks for our substitution. There was 3 marks for working out the change in mass, and 3 marks then for working out the value. So we had 6, 12, so it was 15 in total for that calculation. And then what's meant by pair production was given by 6 marks. So again, when a particle and its antiparticle are produced was 3 marks, and then from energy was another 3 marks. So as I said, that's only part of the question from 2010. Okay. So that example was for pair production. So if we look at the next one in 2012, we're looking at a second example, which is our pair annihilation. So in this one it says, when a positron and an electron meet, 2 photons are produced. So essentially we have the reverse of the reaction of pair production. So we're taking our particle and its antiparticle, and we are producing energy, as opposed to in pair production where we have energy is annihilating or crashing into some sort of a nucleus to produce a particle and its antiparticle. So in this question here, it's asking us to calculate the minimum frequency of the photons produced, and then we have to explain why the photons produced usually have a greater frequency than the calculated minimum frequency that we're working out here. So if you're looking at our diagram to represent pair annihilation, we have a particle and its antiparticle, or in this case an electron and a positron, and when they meet they annihilate each other, and we have 2 photons being produced. So if we were to write that as an equation, we would have the electron and the positron, so E plus being positron and E minus being electron, annihilate, and we end up with 2 photons. So obviously a photon is a packet of energy, and we have to remember that energy of a photon is equal to hf. So in the question then it says, what is the minimum frequency of the photons produced? So obviously we're going to have 2 photons produced, but we're only looking for the frequency of 1. So if we're looking at the energy of the 2 particles together, that would be E equals 2mc squared, and then that would be converted into 2hf. but of course we're just looking for 1, so we can work out our E equals 2mc squared beforehand, and then that would be equal to 2hf after. So we'd have before and then we'd have after. So obviously the 2 actually cancels out, so we don't need to do that. If you do that, obviously just divide by 2. But instead we're just looking for the frequency of one of the photons, because obviously they both have the same frequency. So we can just say E equals mc squared beforehand, and that will equal E equals hf afterwards. Okay, so if we get our E equals mc squared, well, the mass of the positron and the electron, we're not given that year, so we have to go to page 46 in our maths tables to get the mass of the electron. Now, the mass of the electron and the mass of the positron, remember, are the same. So we have 9.011093826 by 10 to the minus 31 times c squared. And therefore the energy of the positron, or the electron, is, so we have 8.198444 by 10 to the minus 14, and that's joules. So of course then this energy, so if I just say that's before and then after, so afterwards then that must be equal to the energy of the photon. So in other words, HF must equal 8.19844 by 10 to the minus 14. So if we're looking for the frequency, then I must divide both sides across by Planck's constant. And Planck's constant, again, was not given to us in the question, so we have to go to page 47 in our maths tables for Planck's constant. So that was for H, that was for the mass of the electron. Okay, so Planck's constant then is 6.6260693 by 10 to the minus 34 in our maths tables. Okay, and then that gives me the frequency of each photon is going to be, so 1.237, and that's by 10 to the power of 20. And of course that's hertz. Okay, so of course if you had done 2mc squared, and then you'd have 2hf afterwards, and we'd have to have the value. Okay, so in terms of values for that question, marks wise, we had 3 for figuring out the mass of the electron from your maths tables. So in other words, getting the mass of the electron from the maths tables was 3 marks. Writing down E equals mc squared was 3 marks. Getting your energy beforehand was 3 marks. Getting your HF, so setting up the equation and finishing off, was another 3. So we had 3, 6, 9, 12, 15 in total for that. 1, 3, 6, yeah. Okay. So what I'm going to get you to do now then is, in your exam papers, you're going to go and have a look at 2003 question 10, 2006 question 10, and 2016 question 12. And you're only looking at the pair production, pair annihilation parts of the question. You're not doing any of the other parts. So you're literally just looking at the theory behind pair production, pair annihilation, and calculation side of it. Okay?